Hello! Within section 3 we are now going to approach the 13th lesson of the course, third of this section, intensity of sound. This lesson is going to be developed based on the headings that we are looking at here, starting now with the nature of sound waves. What is sound? As you can see here, sound is an elastic wave. Type of wave, by how it behaves, it is based on the elasticity of materials. Therefore, it does not travel in a vacuum. It needs a medium through which to propagate. Longitudinal, not transverse, it vibrates in the same direction as it propagates, and three-dimensional, it travels in 3 dimensions, i.e. throughout space. Let's see a small visualization of what the molecules of the medium through which it is propagating would do. Here we would have a simulation of a loudspeaker. This would actually be 3D. There we would have a sphere that would be pulsing. When pulsing, we will see how it hits the molecules around it. These molecules compress the following ones and cause a wave that is traveling, moving further and further away from the source. However, as usual, with any wave we can see that the matter does not travel. The matter oscillates. The matter that is attached to the speaker, to the membrane, continues to oscillate along with it, but the following ones are affected. When the membrane pushes molecules, these cause an overpressure that makes like a balloon. When releasing air, that pushes the following ones. But when the membrane of the loudspeaker moves back, they return to the particles, for example, of the surrounding air, and this causes a vacuum, a rarefaction, that is again occupied by the next one, and so on. This causes, by elastic effects, a propagation of that wave that is, as I say, longitudinal. You can see that each molecule oscillates in the same direction in which the wave propagates. You can also see the typical effect at the more distance. Each time the amplitude is smaller, since we know that it is a spherical wave that travels in the form of spherical fronts. The intensity decreases with the square of the distance and the amplitude with the square root of the square. That is directly with the distance. Remember that the amplitude is proportional to the square root of the intensity. And what kind of wave is the intensity? Well, we can see that it is obviously a wave in which things move. However, it is usually said that it is a triple wave. It is a wave of displacements. It is a wave of densities. And it is a wave of pressures. That is, it propagates as the particles move. It propagates as they are depressed. It propagates as the medium is dense. To understand this triple effect a little bit, let's see it with this one-dimensional simulation. Here we are seeing how the wave propagates. We can see, for example, how J is traveling above some points. That is, the wave travels exactly the same as Amanda and J. However, Amanda and J are putting their views in different places. Let's try to interpret what these places are. For example, let's look here at Amanda and let's look at this particle that is oscillating, which is marked in red. Right now it is in its position closest to the source. We will see that this particle, frame, is moving to the right. And we are going to see when it is in its most rightward position, that is when its displacement is maximum. And we will see that its displacement is maximum just when Amanda is looking at it. There, from there, the ball starts to move already to the left. I rewind, going back to the original situation. Amanda is looking at the maximum displacement. For example, this ball right now is in its rightmost position. This ball is in its rightmost position. If I keep going through this frame by frame, soon Amanda will be on top of the next ball. That means that that ball in this frame is in its rightmost position of its own movement, because each ball does everything a little bit later than the previous one. Also, evidently, there are moments when it is not on top of any of them. It would simply mean that the maximum is that of the unrepresented ball that is just below. What difference does it make to what J sees? J is not looking at the ball at the displacement maxima, but at something else. At what? At the density maxima. What J is looking at is the point where the ball is tightest. This ball, for example, is not tight at its maximum. The moment in which the red ball will be tighter is not here. It is still being squeezed more. It is still being squeezed more. At this moment, it is now is when the ball is more compressed, when the density is higher, and yet notice that it is not the maximum of displacements. The ball is just in the middle of the way and progressing. That is the maximum of density and therefore also of pressure. Then the maximums of density pressure do not coincide with the maximum displacements. You can see that here at a distance length J, look at the following one. That is the maximum of compression, and the same thing if I continue advancing. Let's see when the ball has its minimum pressure. the moment in which the ball is more loose, is curiously, again, the central position, but traveling towards the source, that is to say, in the opposite direction. That is the point where we have the density and the minimum pressure that coincides with the central position of displacements. That is why it is said that we have a wave of displacements, of pressures, and another of densities that are the one of pressures and densities in phase, but the one of displacements is out of phase, 90 degrees pi half radians in a quarter of the wavelength. As we can see looking at the drawings, the wavelength of here, here, and here, this is the quarter. So we have a triple wave. Which one should we focus? All three are simultaneous. It depends on what interests us. For example, in the case of the ear, what interests us is that there is a pressure that moves the eardrum inwards and then a rarefaction that makes it move back outwards, which makes the eardrum vibrate at the same frequency as the source says. And how does human hearing work? Let's be clear that I'm not talking about bats or dogs here. I'm talking about humans, and I'm not talking about devices either. Well, human hearing, our ear is prepared to hear frequencies ranging from 20 to 20,000 Hertz. I am talking about round numbers. It is not exact, and it also depends on the person. There are people who hear, who have a better or worse hearing, which changes with age. There are all kinds. We hope normally we do not hear frequencies lower than 20 or higher than 20,000. If any of you hear higher frequencies, it is for some strange reason. For example, bats can hear up to 120,000 Hertz. If any of you hear 120,000 Hertz, what you must have is Transylvanian DNA. If not, there is no other explanation. Well, dogs, for example, hear lower and higher frequencies as well. That also has to do with how our brain interprets it. What we interpret low frequencies are bass sounds and high frequencies. And high frequencies are high-pitched sounds. We are going to see it now with a simulation in which I am going to provide current to a loudspeaker from an alternating current generator, in which I can change the amplitude of the alternating current, and I can also change its frequency. Now I am going to do it with the frequency. I'm going to start from a low frequency, 200 Hertz, and I'm going to go up, and we will notice how the sound is getting higher and higher. What I have done, therefore, is to increase the frequency of the electric current that supplied the loudspeaker so that its membrane vibrates at higher frequencies that made my eardrums vibrate at higher frequencies. And that has to do the sound louder or softer. That goes with the intensity or amplitude, in fact the amplitude squared. Well, what we can hear sounds from 10 to the minus 12 watts per square meter up to 1 watt per square meter. Sounds lower than 10 to the minus 12, we normally do not hear them. 10 to the minus 12, a number that is important to learn because it is a common reference, is what is known as the hearing threshold. Human hearing does not have to be the same for other species or devices, obviously. This is known as hearing threshold, and it is a way of speaking. Obviously, it depends on the person, it depends on the age, it depends on diseases, it depends on many things, but it is established by agreement. The watt per square meter is what is called the pain threshold. We can hear louder sounds, yes, but I have already said that not for a long time, because we would run out of eardrums, because, well, the pain threshold is something that is not convenient. In fact, even smaller values are not convenient to do for a long time, because they can also be very harmful, but it is convenient to learn these numbers. Here I have marked it in red to make it clear that it is not something important, something I know, come on. I am now going to do the following. I am going to show a video in which I am going to put an amplitude. I am now going to change the value. That is not the frequency, but the amplitude of the alternating current. I will start with a high value and I will lower it. And you will notice the following effect. Practically, you will not notice any change at the beginning. You will start to notice that it turns off at the end. Let's see it. Conclusion. The sensation of progression is not linear. I have changed the intensity in a linear way, and yet I haven't had the sensation of that happening, and that's because the ear doesn't work linearly. Let's do a way of looking at it. Instead of doing an arithmetic progression, that is to say, of making the intensity, the amplitude, the voltages to be 1, 2, 3, 4, 5, 6 volts, I am going to do a geometric progression multiplying by 2, 1, 2, 4, 8 volts. And we will see how doing that geometric progression, my sensation of hearing is linear. It gives me the impression that it grows at a constant rate. Conclusion, I need a geometric progression. that what it means mathematically speaking is that my ear works in a logarithmic form. That is to say that I have to put the values 1, 2, 3, 4 in a nonlinear logarithmic scale. Notice that I am left with the 1, 2, 4, 8, 16 of before. You can see how those numbers in geometric progression do give me a linear sensation. Evidently the opposite happens. If I have an intensity evolving in the form of a line, it gives me a logarithmic sensation. Gives me a logarithmic sensation. For my sensation to be linear, the intensity has to work in an exponential way. That is why we use this concept, the level of sound intensity in which we work with logarithms, to give me the impression that 1, 2, 3, 4, which are logarithms, are a constant evolution. We use this formula logarithm of I divided by I sub 0, where I is the intensity, I sub 0 is the reference, that is going to be the threshold precisely. Be careful. We are talking about decimal logarithm, not Naperian. This is important, especially when we get into calculators or spreadsheets. Second, the I sub 0 is the reference that I already warned before, that we will have to learn the threshold intensity of human hearing, 10, at least 12 watts per square meter. Logically, the quotient of I divided by I sub 0 are the other units. It is a magnitude of dimension 1, whose logarithm is also of dimension 1. In other words, the unit should be the 1 as the coefficients of friction. However, it has a name. It is called Bellio, like the radian is also actually a 1. Is another of the names that are spent for the ones. Although the most common is to spend the 10th part of the Bellio, the so-called decibel, as is the decimeter, the decimeter. How much is this worth for each of the typical intensities? For example, 10 to the minus 12 with 10 to the minus 12, I am left with the logarithm of 1, which we know is 0. That is to say, with this reference, what happens is that we start hearing precisely at what we call 0 decibels. If we do the calculation with a calculator, for example, with the spreadsheet, we get 12 decibels, that is 120 decibels. That is the pain threshold on this logarithmic scale. I am not going to go into more details here. You can look at it on your own to see an example of typical sounds. By the way, it is clear that there are sounds higher than 120, although they do not suit me, of course. For example, the machine gun. Well, there are worse things, obviously, than being behind a machine gun leaving me alone, that I cannot always put the headphones and be ahead. Well, that is another matter. And there are also sounds with negative values, because of course a 10 to the minus 13 gives minus 10. What happens is that I don't care exactly the same minus 10, minus 20, minus 30 than 0, because I don't hear any. So I don't care about other animals, because it wouldn't be so true. And let's finish talking about decibel arithmetic with a series of precautions. If I have two sounds, one of 50 and the other of 55, the result is 105. Notice that I have even put the title in question marks. What are 50 decibels? They are 5 Bellios. I apply this formula. I clear sub 1. How do you make a contrary appreciation of a decimal logarithm? Raising 10 raised to it, so this number is 10 raised to 5, which clearing gives me that intensity. What is 55 decibels? With the same process I get this intensity. What total intensity do I have? The sum of the two. What decibels are those? I do the opposite process and I get that applying logarithm, it is 56.19. And then 50 with 55 is 56.19. Obvious conclusion, this is not true. Arithmetic is not applied. I repeat, arithmetic is not applied to the intensity levels, but to the intensities. Two examples to finish the subject. We have a premiere with 55 decibels, and if it were 100 times more powerful, well, it is not 5,500. Why? Because the corresponding intensity would be this one. 100 times the power, it would give me 100 times more intensity, and the logarithm, being a logarithmic scale, is not 100 times greater. It gives 75 decibels, not 5,500. We have one premiere with 50 decibels. How much should a second one be, so that the two at the same time? Hey, well, if I have 50 to reach 55, I am missing 5. Well, it is not going to be so. Here we have what we have of sonority and the intensity that I have with the first premiere. Below, I have the total intensity that I have to have between the two. What does the second one have to give me? What I am missing to complete? And that intensity corresponds to the fact that the second one alone gives me 53 and 35. No 5. And here I hope these examples make it clear that I can't do arithmetic operations with decibels. They are done with intensities. That's the thing about logarithms. Here you have the usual summary with which I ended the lesson. Thank you very much for your attention.